This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Very bright fellow, has done many very interesting things in his career, especially at Orica Engineering. Finished his PhD in record short time, and also is an excellent orator. And so you'll be able to discover that for yourself as we welcome him here today. Thanks, Peter.
All I can say is, Colin, you don't know me very well yet, after all this time. The content of today's lecture was largely dictated by Dr. Boville. I was going to select a bunch of other stuff, but he asked specifically for some of this material, which is fine with me. Today I want to talk about materials that are used in heat exchangers. Now, heat exchangers are absolutely pervasive. I would struggle to think of any industry anywhere, under any circumstances, that didn't have several heat exchangers. They're all over the place. Your car's got probably 3 or 4 of them, of various kinds. The most common heat exchanger in industry is what's called a shell and tube heat exchanger. Now, shell and tube heat exchanger, as with any heat exchanger, has a minimum of 2 volumes, so arranged with a large surface area between them, so that a hot fluid can transfer heat to a colder fluid. That's why it's called a heat exchanger. One fluid gets heated and the other fluid gets cooled. Now, a shell and tube heat exchanger, there are several types of heat exchangers. There's plate heat exchangers, there are scroll heat exchangers and numerous others, but probably the most common, for a variety of reasons, is what's called the shell and tube heat exchangers. A cylindrical shell with at least 1, sometimes 2 tube sheets, as in this illustration, and a bunch of tubes running between them. If it's only got 1 tube sheet, then they'll usually be U-tubes, in which case the tubes go up one end and do a U-tube and come back and get welded into the tube sheet at the other end. This arrangement that you see here is extremely common. There are squillions of these all over the country, and there, as I say, there wouldn't be a garage, a factory, a manufacturing plant, a hospital, or a car or a vehicle or any piece of industrial equipment without heat exchangers in it somewhere. Very, very common. All right, so these 2 shell and tube heat exchangers, and this particular arrangement, as you can see, there's the volume that's inside the tubes and common to the 2 bits at the end, which are called channels. And then there's the bit around the tube bundle, between the tube bundle and that shell, which is called the shell side. So you've got the tube side volume and the shell side volume, as they're most commonly known. All right, now one of the reasons these are so common is because they're extremely rugged. There are also lots of people that can manufacture them. They're fairly easy to design if you know what you're doing, although a lot of people screw them up quite badly. And I made a name for myself because I could design these reasonably well. But why I could design them and other people couldn't always remained a mystery to me, because it was not difficult to do. They're also relatively simple to build, although a lot of people screw that up as well, only because they're not careful. There are a number of other types of exchangers, such as plate heat exchangers, spiral heat exchangers, and so forth, which are quite difficult and demanding. And each of these has their advantages, but most of the time, shell and tube heat exchangers have the advantage. They're also good for very high pressure and high temperature, or very low temperature as well, so they're quite versatile. They're also tolerant of particulates and two-phase flow, where that's important. That's not always important, but where it is, shell and tube heat exchangers can be designed to take those duties. And they're also most importantly, easy to repair. If you get a whole tube sheet, you can cut the tube out, weld a new tube in, and so forth. So these things are absolutely ubiquitous. You can also make them in a very wide range of materials. Things like plate heat exchangers have only got about 6 materials you can make them in. Titanium, stainless steel, and a couple of others. But shell and tube heat exchangers are made in thousands of different types of materials, because the only requirement is that usually that you can weld it, but you don't even have to be able to weld it to make a shell and tube heat exchanger, because there are other ways of joining the tubes to the tube sheets. All right, now here's an example of some of the things. Here's an acetic acid reboiler. Now this thing was in a plant at Rhodes, up in which is an outer suburb of Sydney, and it was boiling acetic acid, glacial acetic acid. Now glacial acetic acid is called that because when you look at it, it moves like a glacier. It behaves like honey with a whole lot of crystals in it, really slow, gooey, globby stuff. Glacial acetic acid. That is, it's about 95% strength acid. In other words, only a few percent water in it. And the purpose of this thing was to actually increase that percentage. So it goes in at lower concentration, comes out at a higher concentration. The boiling was affected by condensing steam. So on the shell side, there was condensing steam. On the tube side, it was boiling acetic acid. Now, I happened to be visiting this plant for a completely unrelated matter, and while I was there, the plant engineer said to me, "By the way, I hear that you guys can solve all sorts of things. Do you think you could have a look at this heat exchanger?" I said, "Why, what's the trouble with it?" He said, "It falls apart every 6 months." 6 months. And most of the things on these chemical plants are designed to last 20 to 30 years. And if you don't get 20 to 30 years out of them, then they become a consumable item, and it's part of the regular expense. And so anything that collapses every 6 months is a major problem. Now, let me make something very clear here. Large chemical plants, of which this was part, cost an absolute fortune to run. This particular plant costs $250,000 a day to turn off. And therefore, anything that goes wrong, if something breaks down, a pump or a pipe or a valve or a reactor or a heat exchanger, whatever it might be, and it causes the plant to stop, the clock starts ticking immediately. So if you've got a $5,000 pump that somehow malfunctions, and it takes you 2 days to repair it, you're $500,000 in the red. So the cost of the pump becomes almost irrelevant. So downtime usually swamps any material costs, everything. In this particular case, this reactor, it was a reboiler rather, was made of 304 stainless steel. Now 304 stainless steel is the workhorse of the industry. It's vanilla flavoured. It is really common. Probably accounts for about half the total volume of stainless steel in the world. Really common. Costs $5 a kilogram, and it has done for the last nearly 30 years. And that's how much people have screwed the price on it. So it hasn't moved in price very much at all. I mean, it fluctuates, but the mean price over a long time still remains somewhere between $5 and $5.50 a kilogram Australian. So this thing used to fail about every 6 months. They had to replace it. So what they'd done is that somebody had designed the shell section in here between those two body flanges reversible, so that they found that when it was getting close to its failure point, for reasons I'll explain in a moment, they could tip it up the other way and get another 6 months out of it. But it still took them a day to pull the thing apart and tip it up, and then they get another 6 months, then they have to throw away. Meanwhile, they were building another one furiously to put in there. Now, they'd tried other grades of stainless steel. They tried duplex, they tried 316, they tried 904, and all of them lasted around about 6 months. Here's the reason. Now, if I zoom in on a little detail of where that one of those tubes. This is right in on one of those tubes welded to the top tube sheet. There's a level of acetic acid in that tube, which comes to around about 100 mil from the top of the tube. As the steam condenses outside the tube, it conveys heat into the other liquid, into the glacial acetic acid, which boils it. The surface of the boiling liquid is at about 100 millimetres down from the top of that tube. And because that is rather violent, it abrades the material at about that point. So all of the rest of the exchanger was perfectly good, except for this little tiny region about 3 or 4 millimetres wide, where the level was, and that's where they all used to get eaten out. So when they told me about this, I immediately said, well, why don't you use something like a 317 stainless steel, or a 2205, or a 2304, or a 2606, or, you know, and I started rattling off. I said, no, we've tried that, we've tried that, we've tried that, we've tried that, we've tried that. Now, the reason that stainless steel is stainless at all is because it has at least, usually, a minimum of 12, but more typically around about 20% chrome in it. Now, chrome has an affinity for oxygen that is breathtaking to behold. It's very difficult to get oxygen away from chrome. Consequently, when any of these materials that have about 20% chrome in them, the first thing that happens when they're exposed to air, which is always obviously, they form a layer of chrome oxide on the surface. This layer of chrome oxide is typically less than 10 microns thick. It is electronically and ionically very low conductivity, and it also is isometric with the original metal. Now, that's all fancy corrosion speak for the fact that it forms a beautiful oxide layer on the surface that makes it impervious to further reaction, which means that it remains shiny because at that thickness it's transparent and it still looks shiny and nice, and everything's wonderful. And that's how stainless steel works. It's because of the chrome in it, which forms a chrome oxide layer. The problem is, the very fact that chrome is so reactive means that if you abrade that layer, you instantly get more reaction. So as soon as you start abrading the oxide layer on a stainless steel, it will corrode at a furious rate so long as you keep taking away that oxide layer, which is precisely what was happening with this boiling. In other words, the oxide layer wasn't quite robust enough to resist what was going on at that level. Any impurities in the acid would all accumulate at that surface and they would abrade that chrome oxide layer. So the thing just got eaten out. And because you can try all the stainless steels in the world, but they all have the same mechanism for being stainless. And so they all failed at around about the same rate and about the same time. 304 was the cheapest, so that's what they'd settled on in the end, because it gave as good a performance as anything else. So what was I to do? Well, we couldn't change the process much. So what material should we use? If we can't change the process, the only other option is to change the material. Well, one of the other options, the obvious option, is actually titanium. Now, titanium is expensive. Titanium is about 10 times the price of stainless steel. So instead of being $5 a kilogram, it's about $50 a kilogram. So that's rough. But if it's going to save the day, maybe it's worth considering. But when you look at the isocorrosion diagram for titanium, the 1810 is the 304, it's typical stainless steel, and the upper one is titanium. 18.2 is typically a 316, a 303. 17.2, 2.5 is a 316. 2507 is a duplex stainless steel. You can see there's not a lot to choose between them. In any case, they operate at temperatures above that, what it's talking about there. So titanium's not much good. In any case, the oxide layer on titanium is better than stainless steel, but not much. Not much. So titanium probably would have lasted, instead of 6 months, probably 7 or 8 months, but that's it. What I wanted was something that would last 20 years. Same problem. The next selection, which was obvious to some anyway, would be zirconium. Now I said titanium was expensive, 10 times the cost of stainless steel. Zirconium is 16 times the cost of stainless steel. It's even more expensive again. But you'll notice that the isocorrosion diagrams for this are in another league, totally different league. And the beauty of zirconium is that its oxide layer is as hard as corundum. It is magnificent stuff. It's only one step down from diamond. And so it's really difficult to abrade. Not impossible, but difficult. It's also very tenaciously bonded to the underlying metal. Some people haven't heard of zirconium. It's a metal. Element number 40. It is in the same period as titanium and has a number of very similar properties. It is, next one up, by the way, is hafnium. Zirconium has one of the smallest nuclear diameters of any metal, and therefore it's used in a lot of nuclear reactors. Hafnium, by contrast, is an order of magnitude larger, and consequently that is not used in reactors. That's another story, which you can talk to me about later if you're even vaguely interested. What are the properties of titanium, of zirconium? Well, I've got listed 3 here: zirconium, carbon steel, and 316. 316 is another common grade of stainless steel. I've listed the density there. The Young's modulus. Notice that zirconium has half the Young's modulus of carbon steel and stainless steel. I've also listed the thermal expansion coefficient. And you'll notice that zirconium has a thermal expansion coefficient half that of carbon steel and 1/3 that of stainless steel. Very low indeed. It has a yield strength comparable to a bit less than carbon steel, but more than 316. Cost is about, at the time this was, it's now a little more than this, about $70 a kilogram. Carbon steel is about $1 a kilogram. It was at the time. It's a bit more than that now. And 316 is about $7 a kilogram. 304 is about $5 or $5.50 a kilogram. The manufactured cost, which is the important bit, I mean, it's one thing to buy the metal. How much does it cost to actually put together? About $80 a kilogram. Carbon steel is about 8, and 316 is about 14. These days, the cost of the material is about the same, but the labour costs have gone up. For 316, that would now be about $25 a kilogram. But this was the cost at the time I did this job. Okay, you understand? So you notice that, therefore, it's around about 5 times the cost of a stainless steel vessel. But the interesting thing is this. Notice this last parameter, which I've just labelled T, which is the yield strength divided by the expansion coefficient multiplied by the Young's modulus, T on alpha E. Notice that that is huge for zirconium. That number, don't worry about what it means, but that number is essentially proportional to the temperature difference that a zirconium heat exchanger could tolerate between the tubes and the shell. In other words, it's far more tolerant to temperature difference than all these other materials. Far more tolerant. So, as it turned out, at about this time I had been asked by the Standards Association to actually write the Australian code on the design for tube sheets. Now, the tube sheets are these bits here, the bits that the tubes are welded into, and before this time everybody used a document called TEMA, Tubular Exchanges Manufacturers Association, and that gives you very thick tube sheets. If we had to put very thick tube sheets in a zirconium vessel, it would be prohibitively expensive. So I had decided to use some more advanced analysis. If you can approximate that tube sheet as a plate on an elastic foundation, and if you do that, you end up with these equations. Lord Kelvin's modified Bessel functions of the first kind, order 0. And there are two types, Burr and Bai. And that's the solution for that equation in cylindrical coordinates. Very straightforward. Actually, it's not as ferocious as it looks, because those functions are actually double even functions, which means they converge very quickly. You can see the fourth order biharmonic equation at the top, or biharmonic modified equation, the solution there, and the final equation for all the stresses, and so forth. And that's what I wrote into the Australian Standard on tube sheet design. When I did that, that's the document there. When I did that, I was able to reduce the thickness of the tube sheets from 60 millimetres down to 10 millimetres, which reduced the cost dramatically. In a standard tube sheet, drilling the tube sheet is often as much cost as the rest of the vessel put together. Huge amount of drilling time, drilling through really thick tube sheets. With this advanced analysis, I was able to show that the thing was perfectly safe with a nice paper-thin tube sheet. And there's the analysis as it came out of the system. All right, so what were the results? Stainless steel vessel was about $80,000 at the time. Same vessel in zirconium would have been $400,000. A lot of money. A lot of money. By my super-duper optimised design, it only cost $180,000. The annual savings, $250,000 just in downtime, which meant that it had a payback of less than 1 year. When I put that analysis to them, they immediately wrote the cheque for this expensive vessel. And many years later, it was still chugging along quite happily and completely unconcerned by any corrosive effects. Now let me talk about cooling water corrosion. Cooling water corrosion in chemical plants, petrochemical plants and all these other things is probably one of the largest expenses. One of the first things that every plant engineer learns to do and has to learn to do very well is get control of water quality. You can't just put water, because every big chemical plant, every big petrochemical plant, whatever, has this lifeblood running right through it, which is the cooling water. Everything produces lots of heat, and you've got to get rid of that heat somewhere. And the only place they usually end up dumping it is into the atmosphere. So you circulate this cooling water, it goes into a big cooling tower, big evaporative cooling tower, which effectively just dumps all this heat into the atmosphere. These cooling towers are typically rated at things like 64 megawatts, or 120 megawatts, 300 megawatts, depending on what size the cooling tower is. And this is essentially the arse end, as far as heat is concerned, of the entire plant. It's where all of the excess heat from all of the various things that are going on, all the chemical reactions, all the motor power that goes into all the pumps and compressors, all ends up in the cooling tower. Losing control of cooling water is the most common cause of failure in all stainless steels in all the plants around the world. Now, cooling water is usually treated with three things. One is a pH control, to control the pH, so the pH always remains at around about 7.5, slightly alkaline. The second is a corrosion control, which is invariably an orthophosphate dosing of some sort. Calcium orthophosphate, which actually renders many of the carbon steel surfaces with a nice phosphate layer on the surface, which inhibits their corrosion. The pH control is usually done with an amine. The phosphate is for corrosion, and the last thing they have is a biocide. So they usually have to dose the thing with either a standard bromine, or usually these days a chlorine of some sort. In other words, they just put literally gaseous chlorine in the water, and that kills the bugs. If you don't do that, the water goes black within a few days with, you know, all sorts of bugs inhabiting this wonderful warm atmosphere full of all sorts of stuff, and it becomes extremely dangerous. And if you don't treat it with a biocide, you end up breeding cholera and typhoid and heaven knows what else. So they're the three things you have to do to cooling water. They're very tight specs associated with each of them, so the plant works. Now the problem is, because it's going through a cooling tower and using evaporative cooling, this means that some of the water actually gets evaporated, and so you have to make up extra water. So you're constantly putting in more water into the cooling tower. And the water that goes into the cooling tower is just straight out of the tap. And so the stuff straight out of the tap has always got a small percentage of chloride in it. It's always got a little bit of salt. In Melbourne, that is typically around 10 parts per million. In Sydney, it's about 100 parts per million. Most cities around the world control their chloride content to somewhere between 10 and 100 parts per million. After 100 parts per million, you can start to taste the saltiness. It tastes awful. Now the problem is this. As you dose more water into this and the cooling tower's evaporating it, of course the salt is getting concentrated. And so there's usually a limit on how much salt you can tolerate in the cooling water system before you end up circulating a mild solution of sea salt through the system, which is, now seawater is highly corrosive. You only have to look at, you know, handrails and things down by the seashore to see how badly they're corroded, no matter how much they paint them. So chloride attack in cooling water is a really common problem. So you've got to limit the amount of cooling water, the chloride you have in the cooling water. And you do that by blowdown. You bleed some of it off and put it down the drain while you're putting more in the other end, so that you keep, and typically that chloride content is limited, depending on which site you're talking about and what sort of equipment they've got, somewhere between 200 and 500 ppm, which means that if you're cooling water, if your fresh water is coming in at 100 ppm and you can only concentrate it up to 3 ppm, it means that any given piece of water only goes around there 3 times before it's bled off. It depends on how good the water is that you start with. Really common problem. So chloride attack depends on the pH, the temperature, and the chloride concentration, and which steel alloy we're talking about. These are some equations that I developed to help me predict how fast things were going to I won't bother explaining that to you, but that's the critical pitting temperature and the activity of the chloride ion, which is controlled by a number of other things like the PRE, which is the pitting resistance equivalent, chrome content, moly content, and nitrogen content of the steel, plus the pH, and all the parameters are there. The net effect of that is this. If you take something like a 316 stainless steel and you can plot the maximum allowable chloride concentration before you start getting pitting versus the pH for different temperatures, you get a graph like that. Notice carefully what these lines do when I swap to a 304, which has got lower chrome content. You see they jump down? So that a 304, which has got a lower chrome content and a lower molybdenum content, more importantly, won't tolerate as much chloride pitting attack. All right, and there's various ways to use these curves, but I'll tell you a story about them first. One of the problems you have to do is stop too much fouling. One of the problems with biocide, not putting biocide in, you end up coating all the insides of tubes with some sort of slime from all these bugs growing in it, you know, algae and so forth. So you've got to keep the water velocity up, and you've got to keep all the bugs well and truly dead. You've got to make sure there aren't any dead pockets for things to accumulate in and so forth. It's all part of the cooling water design. All right, here's a trim cooler condenser that we had on one of our sites, and this thing lasted almost no time at all. It was only in for a few months and fell apart. It was made of 304, and the purpose of this vessel was to condense nitric acid. And nitric acid is quite aggressive material, very aggressive, highly oxidizing material. And you can see that is a standard shell and tube heat exchanger with ordinary single segmented baffles. That is, they've just got a chop, and as you can see, the water flows in one, up and over each of those baffles until it eventually disappears out the other end. Lots of dead pockets in there, very poor design. Water flow wasn't enough, consequently the temperature on the condensing nitric acid side went up, and there was buckets of corrosion. I was asked to replace this vessel, and I replaced it with this design, which is totally different. It first of all had annular entrance instead of just this little nozzle in the side of the vessel. It had an annular entrance, so you got much better coverage, eliminated the dead pockets. I put the baffles closer together so you get better velocity on the shell side, and we also used a disc and donut design, which gives you better heat transfer, and water flow was also increased 6 times. The net effect of that was that it brought the temperature in the metal down by around about 20 degrees, which brought it within its capability, so it stopped corroding. And that vessel is still operating today. Fitted in the same space that the original one did, by the way. That's quite a tricky task. All right, let's have a look at another example, which is, was not far from here. How are we going? Right. This involved a heat exchanger down at Yarraville. There used to be a chlorine plant at Yarraville. Chlorine is manufactured by creating a concentrated solution of salt, putting it in an electrolytic cell, and you get chlorine gas at one electrode and sodium hydroxide at the other electrode. The gas comes off rather hot. It has to be cooled and dried, and part of this was the part of the cooling system that dried and cooled the chlorine gas that comes off. So it was down at Yarraville, just down here on the river. Now this was the arrangement that was had in a, and you can see that the cooling water was on the tube side, and the chlorine gas was condensing and cooling on the shell side. All right. So the chlorine vapour comes in the top, it condenses on the cold tubes and drops out the bottom at that far. Now that's a pretty graphic. In reality it didn't look quite so pretty, and this was the actual U-tube bundle. It was in carbon steel, it had shed 40 pipe tubes, so it had 2-inch tubes, shed 40, which means that they are around about 4 millimetres thick. I got a call one day saying, we've had a failure of this vessel and we want to buy some shed 160 pipe. Why do you want to buy schedule 160 pipe? Because the stuff they've got there is carbon steel, and I said, which is about 4 millimetres thick, got plenty of thickness. So why do you want to buy shed 160, which would be around about 12 millimetres thick? Hugely thick and terribly expensive tube. So what do you want to do that for? Oh, we've got this thing corroding. It corrodes all the time. I said, why is it corroding? Oh, we don't know. I said, but chlorine gas should be absolutely non-corrosive. To steel, it has no effect whatsoever. You can hold chlorine gas in carbon steel vessels and it never ever corrodes. Unless the temperature gets to 150, then you get a pyrophoric reaction, which is another matter. But here we're not talking about that, we're talking about sub-zero temperatures. At these temperatures and conditions, the chlorine should not be corrosive at all. I said, why is it corroding? Is the chlorine wet? No, we've gone to a lot of trouble to dry it. I said, well, how on earth is it corroding? He said, it's better. I said, oh, okay, so I managed to find some Schedule 160 pipe, terribly expensive material, but they needed it promptly because the plant was down and therefore the clock's ticking and they needed this thing replaced in a hurry, otherwise they'd lose a bucket of money and change a whole lot of customers. So the chlorine is not corrosive unless it's wet. If it's wet, it gets ferocious because then it turns into a mild solution of hypochlorite. But what I found, when I really pressed them, I've almost had to put bamboo shoots under their fingernails to find out some of this information, was it the chlorine that was corroding the tubes or was it something else? And when I found out, I said, no, it was actually corroding on the inside. I said, whoa, wait a minute. The cooling water is corroding the tubes? I couldn't get a straight answer. I said, well, what's wrong with the cooling water? Oh, nothing. There's nothing wrong with the cooling water. I said, but if it's corroding the tubes, there must be something wrong with the cooling water. Is there something wrong with your dosing system, that you have lost control of the pH or something? Because this is right down by the seaside. There's buckets of salt in the air. And if they'd lost control of pH and they'd lost control of their dosing, then they're basically circulating seawater through the system, which would be eating these tubes out quite quickly, which is exactly what was happening. I said, well, why don't we fix the cooling water? Oh, no, couldn't do that. That's huge job. So I eventually put 3 options to them. Option number 1, which was Schedule 160 pipe, very thick, expensive pipe, cost about $41,500 just for the tubes. Delivery was 26 weeks. Ooh, that hurt. Lifetime was about 2 or 3 years rather than the 6 months they were getting at the moment, simply because there was more metal to corrode through, all right? That's all. Option number 2, why don't we go to stainless steel, Schedule 40 pipe? The cost is only $60,000, only slightly more. Delivery is 8 weeks now, and the lifetime is 20 years. That would have worked. In the end, I actually visited the plant, talked to the right people, and implemented option 3. Schedule 40 pipe plus proper cooling water treatment. Cost was $24,500, delivery was in 4 weeks and had a lifetime of more than 20 years. I found out that they had a leak on the plant somewhere, which meant that somebody had a broken pipe and never bothered to fix it, and this water's just gushing out all the time, which means that the cooling water was just rushing out. And to furiously make it up, they'd had this fire hose they put in the cooling water to keep the levels up, which means that they'd given up dosing because they couldn't dose fast enough. Consequently, they were circulating quite acidic and quite corrosive cooling water and destroying their plant in the process. To fix this actually required a level valve and another valve somewhere else in the plant. Fixed it completely. It was less than $2,000 to fix the cooling water system, plus $24,500 to fix the replace thing, and it had a lifetime of 20 years. So why wouldn't you do it? One last one. Cyanide waste heat. Up at the cyanide plant in Gladstone, we have 10 megawatts of waste heat just going up the flue, because I won't tell you why that's occurred. It's basically because of a series of uprates. And eventually there's all this hot gas at about 1,000 degrees just going straight up the furnace tube. Huge waste. Theoretically, this could be used to raise steam and actually recover some of this heat and do something useful with it, like generate some power or whatever. And people looked at this time and time again, so I was asked to look at this time. As it turned out, 10 megawatts of heat going up the stack, you could generate about 3 megawatts of power, and that would save around about $750,000 a year. That's worth having. All right, so the waste heat boiler, you'd have to put that through a waste heat. So you've got to buy a waste heat boiler, you've got to buy a steam turbine, you've got to buy a steam superheater, you've got to buy boiler feed water pumps, you've got to buy a cooling tower, you've got to buy a generator, you've got to buy a gearbox, piping, engineering design, and total cost about $12 million. All right. Anything greater than $4 million is too much for 18% RONA. Now, When you get out into industry, this is one of the holy grails that you'll have to come in and genuflect to at least once a day, usually several times a day. RONA is return on net asset, all right? It basically means if you do a discounted cash flow analysis of the capital versus all the recurrence into the future for the lifetime of the asset, that should balance out at least, in this particular case, 18%. Most companies have an investment policy which essentially reduces to this. What is the minimum RONA that we want before we'll spend money? In this particular case, they needed 18%. And $750,000 a year is not enough to justify $12 million of expense, in other words. It's a bad investment. We could buy it from the local power company at about $31 a megawatt hour. I think it's gone up to closer to 50 since this analysis was done, but the numbers don't matter a lot. So, this particular plant produced nitric acid in another one of the plants, and where you actually just essentially take ammonia and air, and you end up producing nitric acid, water and nitrogen. All right, so one of the other plants needed extra air. Now, the nitric acid plant, the chemistry in them is relatively simple. What it means is for every 4.9 tonnes of air you stuff in the front of the plant, you get a tonne of acid out the other end. Really simple relationship. So the more air you can stuff in the front of the plant, the more acid you get out the back of the plant. So a standard method for upgrading a nitric acid plant is to put a supplementary compressor in to stuff more air into the front of the plant. So one of the proposals here on the adjacent plant, which is sitting right next to it, was to install a larger compressor for 10% more air. But how do you run it? Well, if we put an electric motor on it, then we need more power, and we can get that power from this waste heat from the cyanide plant. So we had upgrade option number 1, a 1.6 megawatt motor-driven supplementary compressor. Option number 2, a larger 3.4 megawatt motor-driven compressor, but then you'd have to put a larger compressor on the thing, but then you wouldn't have to have the complication of controlling 2 compressors running in parallel, which is a non-trivial task. Option upgrade number 3, put a steam-driven supplementary compressor using excess steam from who knows where. That was the proposal. So let's put these 3 options in and have a look at how they stack up. Option number 1 is the 1.6 megawatt supplementary compressor. Option number 2 is the 3.4 megawatt compressor. And option number 3 is essentially option number 1, but with a steam-driven driver. Basically a steam turbine on the front of it instead of the motor, plus a gearbox, because steam turbines usually run much faster than electric motors, so you've usually got to put a step-down gearbox in them. The gearbox, by the way, usually costs about between $150,000 and $200,000 for this sort of size. So it gives you an idea of the sort of magnitude of the money we're talking about. Option number 1 produced a variable cost of $729,000 a year. That's how much it cost. Option number 2 is only $500,000, so that looks more attractive. And option number 3, you save $93,000 a year. So which would you do? Option number 3 also gives you better green credentials, saves the planet, has you buy less power from the local power company, you consume less gas, and you save some carbon dioxide into the atmosphere. What's the obvious choice? You're thinking as an engineer, I can tell. You haven't spoken to too many accountants who genuflect at the altar of RONA. Option number 1 gives you just over $2 million a year profit. Option 2 is $2.35 million a year profit. And option 3 gives you $2.89 million profit. Still attractive? Internal rate of return, which is the RONA, 21% for option 1, option 2 is 16.6, and option 3, 16.2. Which did they choose? Option 1. That's right. The technicalities are irrelevant. It's how much money it makes. Make no mistake about it. Green decisions are very difficult. The only reason people are doing things green these days is because the government is forcing people to pay more for conventional power. Let me illustrate, give you just a couple of simple numbers. The power from a coal-fired power plant is typically in the vicinity of $30 to $40 a megawatt hour. Those sorts of numbers. It's the cheapest power in the world. Don't misunderstand me, I'm not an advocate for coal-fired power stations. I'm just saying these are the facts, right? A gas-fired plant is slightly more because it's a more expensive fuel. That's typically $50 to $60 a megawatt hour. As soon as you go to wind and solar, those things are all well over 100, typically $150 to $200 a megawatt hour, depending on what you do with them, without storage. As soon as you add storage, they double or treble. So why would anybody invest in solar power? It's because the government is actually bribing people to do it by giving them incentives and assistance and all those sorts of things. Now, that's not wrong. That's just a political decision. That's fine. But that's the only way it can be economic, and commercial companies can actually make a buck, because nobody's going to be in business for charity. If you are, you go broke very quickly and then you're out of business anyway. And this is a perfect illustration of that problem. So option 1 here is the preferred option because it makes most economic sense, unless the government gives you some sort of incentive to do otherwise. And that's all. Thank you very much. We have time for a few questions if, in the unlikely event that you're even vaguely interested. Otherwise, please go and enjoy your evening.
Any questions?
Sir?
Can the IRR be higher when the cost lower?
Because the capital is a lot less. One of the distinctions that accountants make is a sharp distinction between capital versus recurrent. And in that particular case, the capital was fairly low, which makes the IRR look high. It's very simple. That's all.
Any other questions for Peter before we let him go home? And you can go to that careers fair.
So, what is IRR?
Internal rate of return. It's an accounting device that you guys will have to have come across very soon. If you don't, go and check it out.
Would you like to just quickly unpack it for the students, Kurt? What IRR means?
Yep. If this is time, and this is expense, in year 0 there might be a large capital outlay, so we've got negative return, and then in subsequent years we've got positive cash flows because we're generating profits. Now these may or may not be up and down. So what you do is if this is year 0 and this is year 1, 2, 3, 4, off for the lifetime of the asset, whatever that is, then we can do a discounted cash flow, DCF, is equal to the sum from 0 to whatever number of years there might be of the cash flow, C, I, multiplied by 1 plus, hang on, CI divided by 1 plus AI to the power of I. A is the discount rate. Now that's typically whatever discount rate you want. Companies vary a bit, but most blue stock companies will ask for a discount rate anything between 10% to 20%, depending on what their investment policies are, all right? And what you do is if you've got a discount rate of, say, 15%, for any given investment, you put it in that equation, and unless this discounted cash flow is positive, you don't invest. Now, let's ask this the other way around. What value of discount rate makes the DCF 0? And that's called the internal rate of return. All right? Go. I know that's been fast, and I know it's got some terrible sigmas and horrible mathematics in it, but...
Don't worry about it further, because everyone who did mechanical design with me had the time value of money, and hopefully everyone's remembering I did.
They should have tattooed on their brain somewhere, should they?
Just that, the Mars bar today is a different
exactly.
than the Mars bar, or $1 in your pocket today is a different value to the $1 in your pocket in 2 years' time.
That's right.
So, yeah, thank you very much. Marvellous presentation. Thank you all for coming, and I'll see you next time.
Always important to mute. That was really good. I enjoyed it. So thank you.
All right? Yep. See you again. Good to catch up with you.
I'll just log out and I forget. Okay. That's on us.